3 p.m. shortly after, so let's get started. Welcome everyone to our distinguished lecture series seminar today. As you know, the DLS seminars are the main high-profile scientific events at our institute, the Max Planck Institute for the Science of Light. And it's a means to engage the most important and influential colleagues in any area of the science of light. Unfortunately, we have moved back from a hybrid event to a full online event. So that means we cannot host our guest here for dinner and have nice lab visits and intense discussions on site. But I think the advantage is that our guests can join from far distances without all the burden of traveling 14 hours or whatever it is between Los Angeles and Erlangen one way. And it's also a good way to open this up for people that are not physically at the institute. So I know that we often attract people even from other institutes. I don't see the participant list right now, but maybe Joyce Poon is joining again with her group. She told me that she's doing that on a regular basis. So hello to everyone this afternoon. It's my pleasure to welcome Aydogan Ozcan, and I hope I didn't butcher your name completely now. Aydogan is a professor for engineering innovation at UCLA, University of California at Los Angeles, head of the Bio and Nano-Photonics Laboratory. He's also professor with the Howard Hughes Medical Institute and an associate director of the California NanoSystems Institute. Aydogan is actually a native of Turkey. He got his bachelor's in science in electrical and electronics engineering from Bill Kent University in Ankara in 2000, before moving to Stanford, where he got a master's and a PhD in electrical engineering in 2002 and 2005, respectively. Did also a short postdoc at Stanford before moving briefly to the East Coast, became a research faculty at the Wellman Center for Photomedicine of the Harvard Med School and Mass General Hospital, and then moved quickly back to Southern California to take up an assistant professorship at UCLA in 2007 and moved up through the ranks to full professor, actually in the departments of electrical engineering and bioengineering and surgery. So a very diverse range of departments that you are a member of. Aydogan has made seminal contributions to computational imaging, sensing, and diagnostics. So very much fitting to the activities that are also going on at our institute. And in doing so, he has covered many diverse topics, which is also reflected in his being a fellow of many diverse societies, ranging from the American Society for the Advancement of, AAAS, SPIE, OSA, also known as Optica these days, IEEE, chemical and physical societies, as well as the Guggenheim Foundation. So very, very interesting and diverse range of societies that you're a member of, actually a fellow of. We've also received a huge number of awards. I think if I wanted to just spell them out all, this would take about 5 minutes. But there were in Presidential Early Career Award, very prestigious, Young Investigator Awards from both Army and Navy, Early Career Awards from SPIE and IEEE, and also an NSF Career Award, just to name a few of them. Aydogan is also very active in translating research from basic science into commercial application. He holds many patents, more than 50, as I understand, is a founder and board member of several companies. And so it's a great privilege and honor to welcome you as a DLS speaker today. We are very much looking forward to what you are going to tell us about diffractive optical networks and computational imaging without a computer. But before I hand over the stage, 2 technical comments. One of them is this seminar is being recorded. So please be aware that by participating from this point on, you will implicitly agree to doing this. And the second one is we ask you to keep your microphones muted during the presentation. You can keep your cameras on, but please keep your microphone muted. If you have a question, type your question or the letter Q into the chat space, and I will call you up and then unmute you or ask you to unmute, and then you can ask your question, probably also throughout, but mostly at the end. So with that, and without much further ado, over to you, Aydogan.
Thank you. So thanks for this very kind, generous introduction, and for having me here. So can you guys see my slides full screen? And as I'm moving my cursor, do you see that as well?
Both.
Great, thank you. So today, I'll share with you our work on diffractive optical networks and how we've been using it as a statistical inference engine. Also, share with you how that's also enabling us to build computational imaging systems without a computer. So before I dive into diffractive optical computing, I'd like to give you a very short top-level overview of some of our research activities. My lab is interested in computational imaging and sensing systems, all the way from point-of-care diagnostics to mobile instrumentation, mobile microscopy, to deep learning-enabled computational imaging. These are, the portfolio of research directions that we're exploring in our lab. We like to fuse machine learning with these instruments to make them more powerful and get as close to lab-grade counterparts that we have. For example, what you have in here is a multiplex point-of-care sensor that is using deep learning as part of its inference. This one, just as a top-level highlight, is a vertical flow assay that you're seeing here. It's an inexpensive cartridge that has maybe 9 by 9, approximately 100 immunoreactions going in parallel from a very small amount of liquid, let's say the serum sample of a patient. And these spots are being imaged and analyzed by a mobile phone to infer a panel of analytes. Here, because the system is inexpensive, paper-based, redundancy is introduced by having the same analyte appear a few places, and this way you can actually use a neural net to understand weaknesses, repeatability problems of an inexpensive test like paper-based vertical flow assay, and bring quantitative analysis through the merge of deep learning and this inexpensive point-of-care sensor. In addition to lateral flow, vertical flow, different kinds of sensing schemes that we would like to work with, we're also very interested in holography, coherent imaging, and utilization of that as a sensor, as a diagnostic tool, especially looking at large volumes of samples, whether it's bodily fluids, water, or air. These are holographic handheld devices that are powered by deep learning because the holograms are reconstructed in real time using a deep neural net, changing our reconstruction engines of the past decade that were iterative, that used basically different kinds of phase retrieval methods. We're now changing them to be powered by deep neural nets to do some transformations to rapidly take a hologram and reconstruct them. For example, this is an imaging flow cytometer. As you can see, it's a shoebox, very lightweight and entirely powered, and all the reconstructions go through a basically local laptop. These are plankton from Los Angeles coastal line that were label-free imaged with a very high throughput with this inexpensive device. On the order of 0.1 to 0.5 liter per hour can be achieved with these kinds of devices. So empowering our measurement tool set in field settings, resource-led setting is a theme in my lab. In addition to that, I'm interested in actually how we can utilize deep learning in enhancing our images. For example, I mentioned in the previous slide how we've been using deep neural nets to reconstruct holograms to empower our field portable devices. But you can also achieve a super resolution to bring, for example, additional resolution from a confocal microscope using a neural net, or take a smartphone-based microscope like these shown here and enhance their resolution and make up for some of the aberrations that they have using a neural net, so that you can match the quality, resolution, and color quality of one of these mobile instruments to a benchtop system as shown here. Perhaps one of the most exciting from the biomedical perspective applications of these cross-modality image transformations that are enabled by deep learning has been virtual staining. This is actually very difficult to establish a forward model because the sample here is a label-free sample. And in this case, we're going to be looking at autofluorescence images, and we'll transform them into a bright field equivalent image of a labeled sample. So virtual staining is all about doing this transformation. And besides a data-driven approach, this is actually a very difficult task to achieve. We're using this to bring contrast to tissue to replace the standard histochemical staining that we have in our pathology workflow, histopathology workflow these days. So basically, the idea is to take autofluorescence images of tissue and train a convolutional neural net coming from ground truth images, coming from literally histochemically stained images of the same slides. We first get the label-free version, digitize it with a few autofluorescence channels like DAPI, for example, and ground truth comes from histopathology. Matching them at these sub-regions of the whole slide, and many of these whole slides, you can actually learn this transformation, which is very difficult to physically create a forward model for. This has been a very successful transformation, not only for H&E stain. These are some examples of salivary gland input images are shown here, virtually stained images, and this is how histochemically it comes from the lab, matching nicely. This is H&E, but you can also do spatial stains, like Jones-Silver stain for kidney tissue. Label-free images are quickly stained to match histochemically stained images of the same tissue. And some other examples are shown here for another type of spatial stain, Mason's trichome for liver and lung. So these are laborious processes, a couple of hours at least for a human histotechnologist to prepare. So we're cutting down time, making it more repeatable. And you can, from a single cross section of a label-free tissue section, virtually create an unlimited amount of stains and that are registered at a nanoscale, from H&E to spatial stains, which is a unique experience for the pathologist. And I think that's why we're very excited about this platform to take label-free autofluorescence images and stain them by passing the entire histochemical staining workflow. And recently we've shown that you can actually do this without any biopsy. This is a different modality. This is a reflectance confocal microscopy. It's specifically aiming skin, biopsy-free skin virtual histology. Here, we're not looking at autofluorescence. We're looking at a stack, a three-dimensional stack of reflectance confocal without a biopsy, and training a network or a sequence of networks in this case to create virtual staining, H&E-like images of the skin without the biopsy. So this is a very recent hot off the oven type of an article that we're very excited about, enabling some of the skin testing, dermatopathology inspection of skin without any biopsies potentially being possible. So of course, these are early stage. It needs to be clinically more rigorously proven. So these were some examples of how we've been enjoying this rich intersection of deep learning and machine learning and optics, specifically for microscopy, mobile instrumentation, mobile equipment, and sensing. So to date, though, after this top-level general overview of some of my work, I'd like to dive into how we're actually using diffraction of light through engineered materials for forming all-optical computers of different kind. And here I'll dive into diffractive neural networks. So in the next set of slides that I'll discuss with you, we're engineering light-matter interaction layer by layer. What you see here at the background are layers 3D printed to work like an all-optical computer at longer wavelengths of the spectrum, terahertz wavelengths. At terahertz wavelengths, these kinds of plastic wafers are transparent. So this is going to form an all-optical network, statistical inference network, that can compute at the speed of light. As light is passing through these passive systems, it will do a certain computation. It's also going to be very useful, not only for statistical inference, but also for computational imaging. You can think of these kinds of diffractive systems as a superset to a lens. They will form computational images of various different kinds, as I'll share with you in the next few slides. And if I have time toward the end of my talk, I'll share with you how you can also use it as a framework for designing non-intuitive optical components, depending on your task at hand, depending on your budget at hand. A diffractive network is, first of all, trained using a computer. You have a task at hand. It could be a computational imaging task, reconstruction of a hologram, for example, all-optical reconstruction of a hologram, or it could be a statistical inference task. The task at hand defines your loss function as a function of which you design these diffractive layers by changing the amplitude and phase values or phase values of these different voxels within that volume layer by layer. As a result, for example, if you're doing a classifier task, this case, looking at, for example, MNIST, handwritten digits, if I shine light through a new handwritten digit, if this classifier is right, at the speed of light, as light is passing through this passive material system, it's going to route most of the photons at the back plane, output plane, to a detector that is assigned to classifier. This is not mode matching. This is not a deterministic task, because once you train it in a computer, you fabricate it and you shine light through new objects that were never seen by the network before. So you wanted to generalize to new types of data to all-optically classify. Advantages are obvious. It's passive. It calculates at the speed of light, low latency, because these are thin optical elements on the order of a few tens of lambda wavelength in axial dimension, and they're scalable. You can fabricate in large areas. If you look at why do we call it a neural net? It's basically, the analogy is the fact that based on Huygens principle, by controlling the phase and or amplitude of all of these secondary waves, you form a network of coherent waves that are superimposed with each other. And by changing the axial distance, you can change the local connectivity. And the math is different than standard electronic neural nets in a number of ways. These are additive bias. These are multiplicative bias terms as opposed to being additive bias terms for an electronic neural net. And except the final layer here, which is the optoelectronic detector, the CMOS, CCD, whatever detector that you have there, except that everything is linear on the front end. The only nonlinearity is occurring when you digitize the detector signals. So I'll share you more about what we've been doing with this kind of a framework. We built initially different kinds of classifiers. For example, the top two rows show us classifiers that are designed to classify handwritten digits. These are the phase layers that we converged in a computer using deep learning-based error back propagation based on classification error. And once you design it, you fabricate it. This is going to operate at terahertz wavelengths. That's why the neuron size here, the feature size of each plate, is on the order of half a wavelength. And the wavelength here is approximately 0.8 millimeter. That's why you can use a 3D printer to show the proof of concept of this. All of these can be scaled down with respect to lambda, and you can have these kinds of ideas operate at different parts of the electromagnetic spectrum. Let's dive into one of these designs first, as shown here. And the idea here is, again, generalization to unseen data of the same data class. If I shine a certain new handwritten digit written by me or you next day, it should classify by routing most of the photons at the back end after light matter interaction to the correct detector. These are examples of blind testing experimentally. Because this system is a coherent processor, you can utilize the phase and or amplitude at the input channel, input field of view, as your information. Here, we're encoding the information in the amplitude channel. And what you see here are test objects, handwritten digits that are encoded in the amplitude of the incoming plane wave. So for example, if I shine number 7, at the output, experimentally, we see that most of the photons went into this detector, which was assigned to class 7. Correct inference done all optically. Similar idea, if I shine light through this 9, there is some background diffraction, but most of the photons, maximum number of photons, go to the correct detector. So this gives you all optical classification. As I said, we have also the degree of freedom that you can utilize the phase channel of the input plane and/or. In this case, it's another diffractive network designed this time to encode the information in the phase channel of the input plane. And this time we changed the task to a little bit more difficult task. It's a fashion MNIST, publicly available data set, which means you have, again, 10 data classes. So you will have 10 detectors at the back end. And each one will be correspond to one of these classes: trousers, sneakers, bags, boots, etc. And the idea, again, to generalize to a new type of a boot, new type of a bag, as I show it without the network seeing it before, it should generalize correctly. These are some experimental results showing how it works with a 3D printed diffractive network operating at terahertz part of the spectrum. For example, if you take this trouser here, if you shot, this is a phase object, this is phase encoding 0 to 2 pi, and most of the photons that it diffracts through it is seen by the correct detector, so on and so forth. This is a bag, for example. Most photons end up here, which is correct interference. So these kinds of systems can be designed with different loss functions. This is a classification task. The results that I've shown you at the beginning were using mean square error as a loss, meaning that we assigned 10 detectors for those 10 classes, and we were trying to uniformly fill in the correct detector for a given type of object, class of object, and looking at basically nice high contrast inference at the back end. Another maybe better way of designing these diffractive networks is actually to use cross-entropy loss, which does not care about the uniformity within the aperture, within the output detector aperture for a given class. It looks at the maximum signal. If you design a diffractive network with cross-entropy, you get a lot more speckly pattern, but you still actually improve, in fact, your inference accuracy by having irregular intensity patterns per detector, but still having maximum number of photons go to the correct class. If you design one of these systems, you can achieve close to 98% accuracy with MNIST data set. These days, we're close to 99%, actually. These are the earlier results. But with proper training using phase and or amplitude at each diffractive layer, you can actually push this system to perform competitively for an easy task like MNIST handwritten digit classification. One of the interesting features about diffractive networks is that they have depth advantage. This means even though they are linear, there is an advantage in distributing your diffractive neurons, diffractive features, one layer after another layer after another layer, as opposed to using them all at the same diffractive plane. There are many different advantages for this. I'll share with you some other advantage in the next few slides. But here we're sharing with you what happens to inference accuracy for MNIST and fashion MNIST data sets. What happens to the power efficiency at the output plane, optical power efficiency, and what happens to signal contrast, meaning that the correct detector versus a competitive detector, second competing detector, strongest competitor, that signal contrast. All of these features, which are good for practical applications, they improve as you build more layers, one following another. It's not contradicting actually anything, despite the fact that this is linear. The system, the optimization framework, likes to work with one layer after another layer, distributing those diffractive neurons in a sequence. You can also visualize a diffractive network as a processor, all-optical processor that can synthesize all-optically any arbitrary linear transformation between an input and an output. So through data, you can actually take any arbitrary complex valued matrix. Let's take an arbitrary transformation matrix with a certain arbitrary distribution of amplitude and phase, and feeding data coming from this transformation from an input field to the output field. You can actually train these diffractive layers to perform that with a negligible numerical error, which means you can synthesize any arbitrary linear transformation. What I show with these different curves is transformation error as a function of number of neurons, diffractive neurons, or cosine similarity, or output error at the output plane of the diffractive network. So all of these curves highlight the advantages of basically distributing the same number of neurons, whatever neuron budget you have, diffractive neuron budget you have. If you distribute them across across different layers, you start to get better approximation power, even if your number of neurons that you have in your pocket is less than NI/NO. And NI here and NO are referring to the number of pixels that you want to transform from the input to the output, which means the transformation matrix size is NI/NO. And even if you have less than NI/NO, you can actually have a very accurate estimation by distributing these neurons that you have in your pocket across a deeper design. And this is shown here, the advantage of deeper design. The error in amplitude and phase of your transformation matrix approximation is going down as I take, for example, even less number of neurons and distributing them across 4 layers, as opposed to using more number of neurons and distributing into a shallower network. You have more error here and less error. The diffractive network like to learn through deeper designs. This is a more easy task. It's a permutation matrix. I'm showing you this after the previous arbitrary matrix, just to give you a little bit more visualization, because a permutation matrix might be easier to visually understand. For example, if you look at here, a diffractive design that has a certain number of neurons with it all placed in a single diffractive layer, its approximation power is not as good. But if you distribute them into 4 layers, you start to approximate much better, despite the fact that you have less number of equations than unknowns, because the field of view, the matrix size here is 64 squared. So just to wrap up this brief intro, diffractive visual computing is a very exciting area. We like it compared to integrated photonics-based processors because visual inputs are already there in the 2-dimensional field of view. You don't need to digitize them. You can process directly on the phase and amplitude information channels of a scene that's directly accessible to you by a diffractive network. Which means some of the more complicated pre-processing that you need to do to deliver the information to, for example, integrated photonic circuit is not needed. All the way from, for example, phase retrieval is a major challenge for optics. You need algorithms to do phase retrieval. Here, the phase information is directly at our hands at the input plane without digitizing or without doing any pre-processing. And another very important advantage of the system is that as I want to process bigger and bigger fields of view, the size of my system is only going to increase linearly. But if you want to digitize it and pre-process it and feed it into integrated waveguides, you will have a quadratic increase in the size of the visual channel. So for certain applications, diffractive visual computing might offer some unique advantages because the information is right there and you don't need to digitize or pre-process the information to feed it to another engine. And of course, it's a passive system. So far, I've been sharing with you some vanilla flavored standard designs. You can also do some more exotic designs and push the inference success of this platform further. One disadvantage of intensity-only detection is that you don't have the full dimensionality of negative numbers, right? So to make up for that, at the cost of increasing the number of detectors by 2-fold, we have used a differential detection scheme where every class is differentially encoded by 2 different detectors. So if I have 10 classes that I want to generalize to, I'm using here 20 detectors and using them differentially so that I can look at positive and negative numbers to classify a certain decision on the spot. And this is a schematic of it. At the back end, you have basically a differential scheme that is looking at the difference, normalized difference between 2 detectors, which will give you the class score. The bigger that difference is, the better the class score, and you can decide on the winner based on which class score, differential class score is better. I'm giving you examples of how the blind inference is working with the differential design for MNIST here. This is a fashion MNIST, this is a bag, and this is CFAR 10. It's a more difficult, more challenging inference task. These are the individual positive and negative detectors that are located here. Reds are positive detectors, these are negative detectors. As you can see, the differential class score is beautifully positive, whereas most of the other class scores are negative. So you have a better contrast, and this actually pushes the inference accuracy of this system. On top of this differential design, you can also spice it up by designing separate diffractive networks that can look at class-specific inference, meaning that you can have, let's say, a few different classes assigned to one diffractive network and a few others to another diffractive network, and they infer in parallel. You benefit from parallelism of optics here, divide and conquer. So basically, the idea is differential class-specific designs are better than standard designs that we have shown. At the very beginning, I've shown you designs that are basically a single diffractive network, not class-specific, that was performing classification as shown here. For example, this is the vanilla diffractive network. By using class-specific differential design, you can improve the inference for all these three data sets as shown here, which is showing you how you can push the inference performance by distributing tasks across different diffractive networks that are class-specific and each performing a differential operation for encoding the class scores. A similar idea benefiting from the parallelism of optics is highlighted here to create an ensemble of diffractive networks that complement each other's decision. Can I create basically an information processor that's going to take the scene, distribute the scene across different parallel channels, and each one of those diffractive networks will be selected to create wisdom of the crowd. I don't need too many of these. The goal here is from a large set of diffractive networks that are individually designed, find the best small group that work together competitively so that you can weigh their scores linearly and have an ensemble class score coming from this group that is designed to work together. Here, we're using a pruning algorithm, which means we're individually designing something like more than 1,200 of these diffractive networks. But of course, that's too many, but you design your set first. And then through an iterative processing, you form these smaller sets with a certain set size that are optimized in the sense that their inference together is improved compared to the best of the group. So you beat the best of the group and you collectively improve your decision making process through the parallelism of optics. So here is, for example, after this pruning algorithm, we've selected here 14 different diffractive networks, all of which are processing the same information in parallel and having their inference scores that are summed up with some weighting scores to give you a final inference. So the idea here is, again, the wisdom of the crowd. This is a CFAR10 data. If you look at the individual components of the diffractive networks here, they're not very competitive. In fact, within that 1,252 diffractive networks, if you just take the best performing ones individually, it doesn't form a good ensemble. It doesn't like to work with the superstars of the set. It works to work with medium stars, so to speak, and bring the wisdom of the crowd. And this is shown here, actually. If you look at the individual scores of accuracy, they're not very high, but collectively they're improving it with respect to the mean of the group, approximately 17%, achieving more than 61% for CFAR10. This was with a certain weight, which means every diffractive network's vote for a given class was weighted differently. So we optimized those scores. And the result is shown here with this kind of a weighting scheme. This is not standard democracy, this is elite democracy. Everybody has a different weighting score. But even if we were to convert it to standard democracy by making these weights all one, you would get a similar actually improvement, slightly worse than what I'm showing here, but from, let's say, 62%, it would go down to 61%. So even if you ignore the weights, you could actually have wisdom of the crowd brought to these diffractive systems. And this is showing you how the selected ensemble size improves ensemble accuracy, the accuracy of the inference for CFAR10. As you can see, within maybe 10 to 15, you have a good jump in accuracy of the inference. For CFAR10, something like 10% jump is really substantial, significant, because it's a challenging task. So In addition to performing inference all-optically, we believe diffractive front ends are also very exciting to perform hybrid information processing systems, where you can think of the diffractive layers that are optimized as a superset to a lens, so that you form a machine vision system where the information is fed through an optoelectronic device, sensor array, to a backend. So you form jointly optimized systems where front end is also trainable through a diffractive system. So in this case, we're looking at a hybrid platform, which communicates with the backend digital network through basically intensity of a focal plane array. Low megapixel compact systems would be one of the most useful applications of this kind of a scheme. The diffractive layers and the backend neural net are jointly optimized for a given task, which means now the diffractive layers do not communicate to us, do not perform single-handedly a classification. Their task is to pass the information within a certain optoelectronic sensor field of view to the backend. I'll give you some examples why this kind of a hybrid system is powerful. And here I'm going to take MNIST again and fashion MNIST classification and build a hybrid system where the backend is very light. I don't want to work with a deep electronic network here. I want to use a lightweight, low power, simple, single fully connected electronic layer. And what I show here is on the x-axis detector array size. So here I'm deeply undersampling by 10 by 10, meaning I'm stealing detectors from the focal plane array. Standard MNIST has approximately 800 pixels, so I'm 8 times approximately undersampled here. Even then, a diffractive front end that is hybrid, jointly trained with respect to the backend, has a beautiful classification, both for MNIST and fashion MNIST. It doesn't get affected by the space bandwidth product of the focal plane array. It works with undersampled focal plane arrays. But if you take a standard imaging optics with a separately optimized system, also fully connected, you get sacrificed in your inference accuracy because of undersampling. So that's essentially how the information processing is understanding through the diffractive network that you are working with limited resources at the focal plane array. Another very important advantage is through this process, not only you have a lightweight electronic neural net at the back end, but also you can maintain its accuracy and have a reduction in energy consumption per image classification. So this is, for example, comparing standard machine vision. Let's say you have a modest network. You don't want to consume too much power at the back end. This is standard perfect camera. And this is a diffractive network with a fully connected back end. We have higher inference accuracy with respect to LINET because of the diffractive front end, optimized to work with the focal plane array. And at the same time, logarithmically, a better energy consumption per image, where you improve both simplicity of the execution in terms of energy consumption, and at the same time preserve accuracy with this hybrid combination. So in a sense, we believe that forming low power, simple systems could benefit from the symbiotic relationship, where the front end could be optimized with respect to a back end, lightweight back end. And we can utilize the superset advantage of diffractive networks to find the most useful channels of information that a backend would like, especially a lightweight electronic backend would like. So this is, I think, one way of designing future machine vision systems to be more portable, lower power, and at the same time benefit from fewer pixels as opposed to many megapixels. In fact, one of that ideas that I just described, we've demonstrated by building a single pixel machine vision system using a diffractive front end. So here, the task is still classification, but this is done in a different way, where we use here a broadband illumination as opposed to single frequency in the past slides. So you have here many wavelengths illuminating at the same time. And the diffractive network here is trained to perform space-to-spectrum encoding. So different data classes here are encoded in the intensity of a single pixel aperture at different wavelengths. For example, lambda 8 here within this broad spectrum corresponds to the class score of number 8. So the idea here is that through this space-to-spectrum encoding, through a single pixel aperture, I'd like to capture a spectrum of 10 wavelengths, and maximum spectral class score intensity will all-optically infer the object type. That's essentially what this system initially does. We've tested this with terahertz. These are terahertz pulsed system. These are the diffractive layers that converge phase-only system. This is, for example, a blind inference showing you the idea. If you take a new 0, a handwritten digit 0, at the single pixel aperture, you have maximum signal to the wavelength that's assigned to this data class. Similar idea for 6. The peak intensity shifts to this, and you can generalize and do this space-to-spectrum encoding for essentially unseen objects. This is also showing you the match between experimental and numerical forward models. One of the most exciting and interesting aspects of this is you can actually take those spectral class scores behind a broadband diffractive network, not only for all-optical single pixel image classification, but also you can build a backhand taking those 10 numbers coming from 10 different wavelengths to do image reconstruction. This is task-specific image reconstruction. From these 10 class scores, you can reconstruct images of the spatial profile of the input field. So this is a symbiotic relationship where that image reconstruction network nicely reconstructs the, in addition to all-optical classification, the seen object. In fact, they form a symbiotic relationship. And I'll highlight the symbiotic relationship right here. I'm giving you here 4 experimental results where 2 of which were successful in this case. 0 and 3. They were having the maximum spectral class score correct. But 9 and 5 were among those that we made a mistake, and we confused them with different numbers. So that's the classification error. But the neural net at the back end, taking these class-specific intensity scores, it was able to reconstruct the images nicely. These are 0, 3, and 9, 5. The 5 wasn't perfect reconstruction, but still, it's telling to a human that this was a misclassification. The interesting thing is that once you reconstruct these images, you can feed them back to the same diffractive network, and actually now the diffractive network corrects its classification. So for 9 and 5, these images were fed, and now the class scores went back to the correct for the bottom 2 images. And again, if you run them through the same image reconstruction network, you get slightly better reconstruction. So this is actually a symbiotic relationship between the backhand and the all-optical front end, forming an interesting machine vision system, all-optical classification through space-to-spectrum encoding. You can also bring the idea of differential detection to this spectral system. In addition to using 10 wavelengths, if you double the number of wavelengths in your system that you want to use, you can assign some of these wavelengths to work as a positive detector and some of these wavelengths to work as a negative detector. You can form differential spectral class scores to improve your inference accuracy. The same idea of contrast enhancement for the correct inference is shown here for 2 different test objects. This kind of a single pixel snapshot space to spectral encoding scheme can achieve approximately 97% using this kind of differential spectral encoding scheme. So these were examples of how we were using diffractive networks for statistical inference at the speed of light using these passive components. Equally exciting to me is the utilization of these diffractive systems as a computational imaging system without a computer, without a digital computer, because we can actually benefit from the idea that the information is already in front of us. We don't have to digitize it. I'll give you an example of what I mean by computational imaging without a computer. Here, we're going to use diffractive networks, not for statistical inference, but for seeing through random diffusers at the speed of light, which means we'll build a passive and scalable diffractive system that's going to see through an unknown new phase diffuser all-optically as light passes from the input plane to the output plane. If you don't have the diffractive network, for a given unknown phase diffuser, the information is lost through the random phase channel. With a properly trained diffractive network, you can bring the information back. Even if this phase diffuser changes in an unknown way to new representations of a random phase diffuser, you'll be able to maintain that generalization to the reconstruction, all-optical reconstruction. To do this, we're taking MNIST data here to teach the network how to image things. But different than a standard imaging system, we're constantly changing through the training phase the phase diffuser in this system. During one training phase for a diffractive network, we're using many of these different random phase diffusers. We call them known because we've used them during the training phase. So there are capital N known diffusers that were used to train this diffractive system to penalize it every time it couldn't reconstruct it nicely. At the end of the day, once it's done, I'm going to test it with some blind new diffusers never seen by the network before and compare the performance of known versus unknown diffusers. Once it's trained, this is, for example, how you reconstructed the backhand output plane of a diffractive network for known diffusers. K refers to the known diffuser numbers here, 3 examples. And these are the blind diffusers never seen by the network before. Each one of these are unique representations of random phase patterns that were not used during the training phase. So it generalizes. I'll quantify how this generalization works, but let's start with this one. This network was trained with MNIST, meaning that it has never seen gratings. So it generalized to actually resolve gratings of different kind, both through known diffusers that were used during the training phase and blind diffusers that were first time being tested. And these are showing you the resolution test target period versus the measured grading nicely, basically resolving these features. And again, these kinds of test objects were never used because this was purely an MNIST training strategy, MNIST-based training strategy. So this was tested with random phase diffusers in an experimental system. If you look at the diffractive layers that we converged, they look like this for layer 1 to layer 4. I'll come back to what I understand from these diffractive layers in the next few slides. So bear with me for the time being, but I'll come back to these layers. So these are some experimental results where we shine 3 representative examples of MNIST and different gratings, both through blind diffusers, new diffusers never seen, and known diffusers. You essentially experimentally see that it's working. Although the contrast is not as good because terahertz systems have a lot of wavefront issues. So the experimental results here are much more challenging than the previous numerical simulations because of the lack of proper components in terahertz waves in terms of wavefront stability and focal plane arrays, stuff like that. This is a very interesting slide that is telling you how this generalization performance is a function of number of diffusers used in the training phase. If I use a lot of known diffusers during the training phase, let's say 1500 to 2000, this is the signature of almost a perfect generalization. If you look at these color bars, I'll explain what they mean. First of all, this is the blue one, which is showing you the known diffusers from the last epoch. A better performance of reconstruction with the blue is memory. The network memorized the last diffusers in the last epoch. That's why it's performing very well. How well? As if there was a node diffuser. So if you look at the purple here, it's showing you what this network would do if I take off the diffuser, random diffuser there. This is what it would do. It's a certain imaging system. But the good thing is that it memorized the last few diffusers, and the blue bar of a good design is as good as no diffuser. If you look at the orange and yellow, they're about the same for a well-designed one. That means the new unknown diffusers are as fresh as some of the known diffusers from the previous epochs. So it generalized basically to new diffusers and also works as a general purpose imaging system. It works even if you take off the diffuser. And if you use fewer diffusers during the training, it doesn't work well. And you can understand that from the poor performance of the orange and yellow here, and also overfitting to the last diffuser. So this system, which was only trained with 100 diffusers during the 100 epochs, unfortunately didn't work. You had to go up to maybe 1,000 to 2,000. The reason is it's overfitting to basically the loss diffuser, and the memory, you cannot forget that memory in this sense. So let's come back to a little bit more about how the system is working. If I take a design without any diffuser and try to form a compact imaging system where sample to image plane is a few tens of wavelengths, this is the diffractive layers that you convert. This is training without a diffuser. If you zoom into one of these diffractive layers, you form here through data an imaging system where if you zoom in, you see these pockets of phase. This is like a basically micro lens array. The network, through error-back propagation, learned to pack these micro lens arrays into each plane to make up for diffraction, loss of spatial information. And this is actually a micro lens array, one following another, without any diffusers. If you look at what happens if I start introducing random diffusers to generalize to see through these diffusers, this is what you get. So if you look at the diffractive layers of the system trained through to see through diffusers, there is some micro lens array formation. You can see these phase islands, very much like that. It's packing, but there are other phase features in between. So it's the collective relationship, symbiotic relationship between those micro lens arrays and the surrounding phase perturbations that are helping to reject the scattering light and having the forward least scattered light to form an image of the scene. It's actually a very interesting observation in the sense that the physical laws of imaging are encoded through your optical forward model and data, and the network understands how to kind of optimize a solution based on your task. I'll finish up in the last 2 minutes or so with another interesting application of this framework to perform a computational imaging task. And here I'll show you results from solving or reconstructing, all-optically reconstructing a hologram. So if I have a hologram, which is an intensity-only recording, you need to perform phase retrieval to recover the object of this hologram. And that process in itself is as complicated, sometimes equally complicated, as seeing through diffusers. It's done today with a lot of iterative computation. Deep neural net has been revolutionizing that field as well, but still you need a digital computer for that. So the goal here is to reconstruct a hologram all optically without any iterations as the light is penetrating through. This system is trained with 3 different loss functions. One of them is structural loss, one of them is a Fourier loss term, and the other one is diffraction efficiency loss term. One of the beautiful things about deep learning, data-driven design is you can actually mend the loss function depending on your interest. Not only maybe structural performance, but also diffraction efficiency in this case could be fine-tuned. And what I'm sharing with you are some test objects never seen by the network before. This was trained again with MNIST data. Holograms look like this at the input plane, encoding the phase and amplitude information. And at the diffractive network output, you have a single pass through the network, revealing the intensity or amplitude distribution of the object beautifully well at the back end. Interestingly, it also generalized, just like any other holographic reconstruction should be. It generalized well to other types of objects. So we've never seen any of these types of clothing, but you have these objects now from their holograms beautifully reconstructed at the back end of the network. So it generalized very well to different types of objects. So one of the interesting aspects is this design space. So there is a trade-off between how well your reconstructions can get and diffraction efficiency at the back end. And by playing with these relative coefficients in your loss term, you can find different diffractive designs. All of these points are different solutions, all-optical solvers for a hologram. These are structurally better, but poorer efficiency. And these are structurally slightly worse, but much better diffraction efficiency. Depending on how much SNR you have in your detection system, you can actually fine-tune and operate somewhere in between these points. And that's actually another very exciting, in my opinion, aspect of diffractive design. Depending on your budget, you can fine-tune where you want to operate. So I'd like to conclude here. I have more slides, but let me go to my final slide. So Diffractive networks are forming an all-optical computer or a superset to a lens, so that they can actually form hybrid systems that pass the information to a backend, or all-optically can perform certain inference tasks at the speed of light using passive components. In my opinion, one of the most exciting aspects is being passive. You fabricate these things at different parts of the electromagnetic spectrum, and they would work. And if you need to repair them, there are ways to repair them, like a Lego-like transfer learning process, taking off some layers and putting some new layers. In addition to being utilized as an all-optical inference or hybrid system, passing the information to a backend, we believe that diffractive computing also is going to be interesting, finding utility, interesting uses for computational imaging. And I've given you examples of that in the previous few slides. And finally, although I haven't talked about it as much as I wanted, you can also design optical components. Give me a certain design constraint in the spectrum, in the spatial domain, or both. We can actually design diffractive systems that will be non-intuitive and satisfy your design matrix, design constraints budget, so on and so forth. So that's why we're very excited, and I think this is going to be also potentially finding applications in microscopy, in sensing, defense, potentially robotics, you name it. So, of course, these are basic research elements. There's a lot more to be done to bring these into visible or near-infrared wavelengths. With this, I'd like to conclude. Once again, thank you very much for having me here today, and I look forward to your questions. Before I conclude, I'd like to also acknowledge all of our funding agencies, researchers, undergraduates, postdocs, graduate students behind this work. Thank you very much.
Everyone, thank you very much. That was a fantastic talk, very, very interesting. There are a couple of questions lined up already, but I have a very basic questions maybe to get into the Q&A. So I understand that you do the computation of your diffractive elements on a computer, and then you print them in physical form, right?
That is indeed right.
Yeah, so you have static diffractive elements at the end. What's the advantage of doing that over, say, using an SLM or something that you can then also dynamically change with time? Could there be interesting applications of, I don't know, feedback and using that for improved learning in some way, also including that into your learning process, etc.?
Absolutely. I think spatial light modulators, people have already started to use cascaded spatial light modulators to do what I'm showing you with static layers. So it's that, you know, there are pros and cons. Spatial light modulators are great, but they're still consuming power, and they're still relatively bulky. And cascading one after another, very closely spaced on the order of a few lambda, because our designs are to be, you know, for some of these designs we're talking about a few lambda to a few tens of lambda spacing between diffractive layers. If you want to have passive, no power consumption, monolithic design, like a piece of glass, that want to compute something repeatedly, I think having passive systems, I like it. Yes, they're not reconfigurable. If you want to reconfigure them, you can perhaps have one spatial light modulator as part of a system that could be retrained as your data change or as your task change. So they have pros and cons, right? And I think a lot of researchers in the field have picked up on the utilization of spatial light modulators and cascading them to form these kinds of diffractive computing hardware. And I like that direction. But personally, I'm very intrigued with maybe from you know, my previous research on resource limited sensing and imaging. I like things that are passive, that do not consume power, and very compact. One of those things, for example, here, it may look too big to you, but this is only 50 lambda in thickness. If you think of it and operating in the visible, you're looking at you know, 100 to 150 microns of thickness. And that's what I like about passive systems. Of course, they have their disadvantages, not being reconfigurable, and so on and so forth.
Right. So maybe a very quick follow-up question. And okay, so I understand that it's cost of energy efficient to have a static passive optical element. Do you think this could be placed in front of any imaging system? For example, I don't know, think of autonomous driving, right? you have cars driving around, they need to process visual scenery. Would it help to have these diffractive elements in front of the cameras to already do some sort of routine improvement of the data so that the computational processing becomes a lot easier afterwards?
This is one of the premises of the hybrid systems that I've mentioned. Imagine a system that is normally formed by a lens array. Like, let's say you have a lens, a compound lens. You take an image, a few megapixel, and then you upload it in the cloud or locally in the machine, in the vehicle, you do processing. That's, I think, a little bit of inefficient, right? You digitize unnecessary information, in my opinion, because it's a task-specific computing that you want to do. Let's say you want to recognize stop signs, or you want to recognize pedestrians based on a certain, infrared spectrum. If that is your goal, I think communication with many megapixels is not a good idea. And that's exactly what I'm showing here, pointing to an opportunity where diffractive front ends before a focal plane array could be forming more task-efficient, jointly optimized systems. And this is also highlighted here. Imagine, this is MNIST and fashion MNIST, but let's say this was stop sign related, traffic light related thing. What I'm showing here is that you don't need as many pixels at the focal plane array to start recognizing these objects very accurately. For example, this is an image that naturally has 800 pixels for both of these data sets, fashion MNIST and MNIST. With only 100 pixels, you can actually communicate to a backhand, very lightweight, fully connected, single fully connected layer, and achieve something like 99% almost accuracy with MNIST. And I think that's a very valuable proposition. Two things happening at the same time. Cut down megapixels or number of pixels you capture per snapshot, meaning that you can now operate at higher frame rates, lower power, and you don't create a data bottleneck. And second, the backend can also get lighter. You don't need a deep neural net because computation is jointly done through both optical front end and a backend. I think that's a value proposition. It needs to be cooked more, of course, and I think explored more in terms of what kinds of utilities we can bring for autonomous driving and other applications for these kinds of ideas.
Yeah, thank you very much. I should monopolize the questions here. Florian had a question.
Okay, so thank you also from my side for the very interesting talk. I would have several questions, but I confine myself to one. So there was a very intriguing result at some point on the optoelectronic part, the hybrid approach, where you want to combine the optical part with the network, and you have made a comparison where the thing you compared against had one of these earliest convolutional networks, the LENet, and that had, of course, larger energy consumption, which is kind of reasonable, but also less accuracy, and that intrigued me. Can you explain this? Absolutely.
The less accuracy is because of the detector size. We're undersampling it. I'm giving you an example along the same lines of what I've answered Johan's question. Here, we're pushing the network to work with an undersampling focal plane array. You don't have the same 28 by 28 focal plane array here. You only have 10 by 10. And that's where this is losing, because its front end is an imaging optics, meaning that you have a perfect camera there, but the focal plane array is not resolving everything because it has only 10 by 100 pixels. And that's the resolution loss that drives this inference accuracy problem. The diffractive front end, since it's not trying to project at the same scene as it is to the focal plane array, it's communicating with those 10 by 10 pixels better, and then not penalizing the backhand fully connected layer for undersampling.
Oh, I see. Oh, you could even view it a little bit like autoencoders. There's a bottleneck with the 10 by 10, and okay, I understand very well. Okay, thank you very much. Very good.
Thank you.
We'll have maybe two more questions, not to extend this for too long. I know you have other appointments. So there's one by Gian Maria Calizesi. If you unmute yourself and ask your question.
Okay, can you hear me?
Yes.
Okay, so I was thinking about performing other operation without diffractive network. Like, for example, in order of principle, diffractive network, deep neural network have been used for like lots of tasks in imaging. So I was thinking about using this kind of hardware-built network for performing live tasks, for example, in imaging, like fluorescence microscopy, or like, let's say, some more difficult task, like the convolution task. I mean, it's something that you have a priori information, I mean, in terms of point spread function or whatever. So I was thinking about, what about using diffractive neural network to do this kind of task? And how does, I mean, would it be possible in terms of light efficiency?
Great question. So fluorescence objects would probably be challenging the current state of diffractive networks in two ways. First of all, the light is broadband and it's incoherent. So you lose. So a diffractive network is a coherent processor. If you have information in phase and/or amplitude, you know it's working at its best. It can also work with only intensity, only encoding, and certainly fluorescence light could, in principle, work. Broadband, relatively speaking, and incoherent, you can make it work, but you lose some of the advantages. And I think one of the challenges for fluorescence would be signal-to-noise ratio because of the weaker aspects of the emission. However, I think I foresee holographic coherent imaging methods to be integrated with basically diffractive systems. And I think this is something that I'm personally interested. It's a fabrication challenge because whatever I've shown you were relatively bigger wavelengths. Now, everything needs to go to sub-micron dimensions in terms of the pixel pitch. Pixel pitch is half a wavelength approximately. So once we design compact diffractive systems, at least composed of maybe two layers that operate at visible wavelengths, somewhere between, let's say, 400 nanometer to 900 nanometer range, where CMOS images work. I think I see a lot of interesting applications for cell biology, for incubator-based imaging, for certain tasks. You can think of them as live data, say, or things that you need to repeatedly do, right? Within an incubator, is there growth of some unwanted things? You don't want to digitize the entire thing within an incubator and constantly run deep neural nets. It's going to be too costly data-wise and computing-wise. I foresee applications where these compact systems can be utilized to do repeated tasks for cell biology and life sciences-related applications. It's something that I'm working on, but it has to be miniaturized, and it has to, most likely, it has to be merged with coherent illumination, partially coherent maybe, light-emitting diodes, laser diodes. I think that's going to be the first stepping stone. Holographic quantitative phase imaging and using that quantitative phase information to be processed by the diffractive network. That's something that I'm actively working on, very exciting area. It fully utilizes the benefits of diffractive front end. Fluorescence could be, I think, another milestone after that, in my opinion, because of the challenges, signal-to-noise ratio related challenges. But coherent will come, hopefully, a visible based quantitative phase imaging will be coming.
Thank you for your answer and for your talk.
We'll have one quick final question by Fabian Wohlfahrt. So I don't know if Fabian is still here. I mean, maybe he cannot, doesn't have a phone, or he cannot unmute, so I can read it out. How high must the printing resolution for the diffractive elements be to reliably reproduce the computer simulations?
That's a great question. So, each diffractive neuron of a diffractive layer, for example, if you look at this slide here, there are 40,000 neurons here. This is, a modest size network where with 5 of them you have 0.2 million trainable phase elements, each one 40,000, 200 by 200. The feature size here is wavelength divided by 2, half a wavelength. If you're operating at, let's say, 1 micron radiation, you need to have half a micron pitch where you change the phase. You can use metamaterials, you can use different kind of lithography tools, two-photon polymerization, etc. Here we were using 3D printing because our wavelength was on the order of a millimeter. So that's what it is. You need to have a sub-wavelength resolution. But that doesn't mean you cannot build a system that operates with bigger neurons. Actually, you can. If you go to lambda by lambda or 2 lambda by 2 lambda neuron size, you sacrifice, you still work very well in the sense that you lose your degrees of freedom, you lose your numerical aperture a little bit, processing capability. Instead of using the full number of modes in free space, you use smaller number of those modes and control their amplitude and phase. But still, it depends on the complexity of the task. You can operate with bigger diffractive neurons. Lambda over 2 is for us to utilize the full space bandwidth product between the diffractive layers, but you don't have to operate at that level. I want to also mention one thing where we introduced during the pandemic, we introduced vaccination to these diffractive networks. It's not the same vaccination, but the idea here is during the training phase, we take into account potential misalignments. Not shown in my slides, but you can find, if you type vaccinated diffractive networks, you can find some papers from our lab on it. Basically, the idea is, just like vaccination, you introduce some villain through the training process and on purpose, laterally and axially misalign these diffractive layers to a certain range. Depending on your tolerance in terms of alignment, you set random variables between this diffractive layer and that diffractive layer and do this repeatedly. If you look at the diffractive maps after this training process, it's smeared spatially around the detectors and around the decision-making points. It's got some slower variations. It's smearing, and it's shown actually with very little compromise in inference accuracy. You build a system where you can on purpose misalign and it still infers. So those kinds of ideas are also available to push fabrication, the practical applications to be tolerant to fabrication or other types of misalignments of the system. We call them vaccinated.
Okay, I think we'll stop here with questions. Thank you, Aydogan, very much again for this wonderful presentation. Very stimulating research. Always great what is coming out of your lab. So thank you very much for joining us today. And
thank you for having me.
Virtually, I represent everyone else. Thanks. And thanks for everyone else for joining in today. Have a great afternoon.
Thank you.
You have a meeting with Florian Marquardt now, right?
Great.
And you should have received a separate Zoom link to meet him.
I thought every link was, let me check what Lisa sent me quickly. I wasn't sure if it was a separate link or the same link.
If you don't have it, I can send it to you.
I have it actually. Okay, I got it. Yes. So yeah. I'm going to connect through this.
So out of here and into the next room then.
Okay.
I'll see you in half an hour or so.
Thank you.
Thank you.
Take care. Bye.